Almost every piece of electronics around you starts with this. This is a breadboard. It's like the Lego base plate for electronics, but instead of stacking bricks, you're connecting wire and components to bring your ideas to life. And just like with Lego, after you build something, you could take it apart, rebuild it into something new. It unlocks your creativity so that you can invent your own circuits and devices, anything you can imagine. In our last video, we built a basic LED circuit, 5 volts to the LED to the resistor to ground. But now we're going to make it better and more flexible by using wire and adding a button. Then you'll know how to customize and make your own circuits. What you'll need: a breadboard, some simple components like resistors, LEDs, and a button, wire, and wire strippers, and a source of power like an NLAB. First, I'm going to destroy a breadboard to show you how it works on the inside. Then, we'll talk about best practices like color coding. Then, you're going to make some wires and add a button. And finally, we'll show you what a short circuit looks like. Let's start by taking apart the breadboard and seeing how it works on the inside. Under the plastic are metal strips for the wires to touch. When you want 2 wires to touch, they need to be touching the same piece of metal. The center of the breadboard are 5 holes in a row, and under those 5 holes are 1 piece of metal. So by plugging a wire into any of those 5 holes, and then a second wire into that row, they'll be touching because they're touching the same metal bar on the underneath side. But notice that the breadboard is actually 3 different pieces of plastic. So because it's 3 different pieces of plastic, we can tell that the holes in the columns are never touching the holes in the rows. The holes on the sides are connected in columns, the holes in the middle are connected in rows. Also note, in the middle of the breadboard, the row has a break in the middle, so the 5 holes on the left of the row don't touch the 5 holes on the right. But if you wanted to make them touch, you would have to use a wire. We're going to come back to that. When we build circuits, we usually need lots of holes that give us power and ground. So we'll use the rails for that. When you use a device like an NLAB, it puts 5 volts and ground in the columns on the right, and minus 5 volts and ground on the columns on the left. Then you would use the middle part of the breadboard for connections that are not power and ground. So if we're building our red LED circuit, where the LED touches the resistor has to be the same row. It doesn't work if it's in the same column, because these 2 rows aren't touching. It also doesn't matter if the resistor touches to the left or to the right of the LED. As long as they share the same row, they're touching the same metal bar underneath. So why is wire important? Well, in this flashlight, the LED's at one side, and the button's at the other, and the battery's somewhere in the middle. It doesn't make sense for them to all be on one side or the other. So that means we need to make the connections between all 3, and we'll use wire to do that. On my breadboard, I might want to simulate this a little bit better by doing the same thing. So I might want my resistor to be, over here, and my LED to be here. Now I'm not taking advantage of the power rails anymore, so I need to make those connections. I need the 5 volt and the ground and the connection between the LED and the resistor. I'll use wire to do that. I like to make my wires from scratch. That way they're the exact right size and color-coded so I know what they do. You can buy pre-made wires that look like this and this, but then your circuit ends up looking long and loopy. It's hard to follow when the circuit is complicated, the wires fall out when you take it in and out of your bag, and they're not color-coded. So when I make my wires, I'm going to use red wire for 5 volts, black wires for ground, and then I have all the other colors for the other things in my circuit. This is kind of an industry standard. For low voltage circuits, we use red wire for power and black wire for ground. And I'll try to make my circuits flush against the board and at right angles. We call that Manhattan style. Manhattan style means at right angles, like navigating the grid-like streets of New York City. That way, they won't fall apart very easily in our bag, and they'll be easier to read. So how do I make a wire to use in my breadboard? Well, first I need to cut it to length, and then I need to remove the insulation so that the wire could touch another piece of metal. To make that wire, I'll use these wire cutters and strippers. This is the cutter, and these are the strippers. There's also some pliers at the end. To use them, give the handles a little squeeze and undo the thumb lock. Always click them a few times for fun. We'll start by cutting off a few inches of red wire. The thickness of the wire is called the gauge. We want to match our wire to one of these gauges. If you don't know the gauge of the wire, start in the middle. Try to clamp down on the insulation. It will cut through without nicking the wire on the inside. Tug on the wire and the insulation should just slide off. If you pull hard enough, you could probably get it to come off. But if we use the right gauge hole with the right gauge wire, it's a lot easier and it slides off very easily. If you use a gauge hole that is too small, it will cut through the insulation all the way, but then also cut into your wire. You can see I nicked the wire. The wire is now going to break at that spot, probably at the worst possible time. So we want to figure out which size works best for the wire that we have and use that one. The amount of insulation to remove is about the depth of the breadboard, so that when the wire is plugged in, there is no exposed wire. If you strip too much insulation, the wire could touch another wire, and that would be bad. and if you don't remove enough insulation, the wire won't be able to touch the metal inside the breadboard. Now let's complete our LED circuit. We need a red wire to connect to 5 volts. I'll measure my red wire to connect to 5 volts. Strip off either end. I measured that length of wire so that it would be as flush as possible against the board to make the connection. Now we need a black wire to connect the resistor to ground. So I'm measuring, cutting, stripping, bending, and plugging. The last wire connects the LED to the resistor, and I could use any color of wire for that. I'll use a yellow wire. Measure, cut, strip, and connect. And we've got our red LED back on. Now, if I'm unhappy about how long this yellow wire is, I can remeasure it, cut, strip. Well, now it's too short, but I can bend my resistor to make up the space, and we're back on. Let's think about how we could add a push button to this circuit. A push button is a wire that is broken, and when you push it down, it connects, and when you let go, a spring pushes it back open again. If you want, you can fake a button by sticking 2 wires up in the air and touching them together. This brand of button has funny feet. They're too big to fit in the holes of the breadboard, so we have to cut them out of the cardboard. Let's do a mini experiment. Can you figure out where to put a button in between the LED and the resistor so that when you push the button, it turns on the light? Take a second to think about it and build it. I'll wait. Okay, how did it go? Let me show you how I did it. So, if we break the circuit open and add the button, the goal is that when I push the button, the LED turns on. I should draw it so that I could follow along. Here's my original circuit. Now what I want to do is add the button in between the resistor and the LED. So the LED will only be on if I push the button connecting this wire. So to finish my circuit, I need some wire that's going to connect the red LED to the button and the button to the resistor. Super cool! Why don't we try to design a more complicated circuit? What I want is the LED to always be on, and when I push the button, I want the LED to turn off. So basically, it should do the opposite of what I have right now. I'll pause here. Why don't you think about it, build it, and test it, and we'll see what we can come up with. So how did it go? Hopefully your first intuition was to draw it. That way, you'll have something to reference as you're building. I solved this problem by adding the button across the LED. Now, when I push the button, the current will go around the LED through the resistor to ground. So if no current goes through the LED, it won't light up. But when I'm not pushing the button, it's like it's not even there, and the LED will be on. I can do a quick demo to prove that. I'll go back to my original circuit. The LED is always on, and if I put a wire from one side to the other side of the LED, the current bypasses the LED, the LED is not on, and the circuit isn't broken or anything, it just means that there's no current going through the LED, so it's not on. Still works. So how about I build that from scratch? So I've prepped all my parts. We'll just follow along with the diagram. So 5 volts from the rail into the breadboard. The long side of the LED to 5 volts. The button in the exact same rows as the LED. The resistor touches that row. The other side of the resistor touches ground. I turn on my power, and the LED is always on. I push the button, and the LED is off. When you push the button, you're creating a short circuit around the LED. A short circuit is a shortcut for the electricity to take around part of your circuit. So when you push the button, the LED gets skipped over. Short circuits can be really big, like when a storm knocks out the power to your house by touching the power lines together. I hope you enjoyed learning about breadboards, wires, buttons, LED circuits, and the importance of drawing things before we start building. Now that we have these basics down, we can start covering other topics like what is voltage, current, and electrical power, and how do we design functional circuits like a thermostat or an extra bright flashlight, and how do we get control over our electronics by building them from scratch and understanding the design. Thanks for watching. See you next time. The sides are rails. They're connected as columns. The middle are rows.
Connected by rows.
connected by rows.
I do like to sing.
That would be pretty fun.